Okay, we're back. So we're going to do some laws. Laplace's law is P equals 2T over R, where R is radius, T is tension, is how I think of it. It's like if you have a circle, this right here is your T, and then the pressure that pulls in is your P. So that's the pressure. So that's Laplace's law. I don't really know why it's relevant, to be honest, but that's what it is. For alveolar gas equations, so that's going to be your P alveolar whatever is equal to your FiO2 over the pressure of your atmosphere minus your water minus your PCO2 over 0.85. This is just a normal ratio that we've calculated for all humans. Basically, this value right here is the value of oxygen. It's the partial pressure of oxygen in your alveolus. And because it equivalates with our blood, this number should also equal your P little a for your alveoli. So if your usual one is 0.21 for the oxygen, this is 760, this is 50, and then that should be 40. If all of that matches, then your value should be about 102 in your big A for your alveoli, which means that it should also be 102 in your blood, right? That should be the partial pressure. So the clinical application is that if these two don't match, well, then something's getting in the way of this transport. Either there's fluid in the lungs or something of the sort. So that is why that is relevant. Breathing rate is another one. Okay. How is CO2 and oxygen transported in the blood? So oxygen, 98% of it is attached to hemoglobin. Like most of it's attached to hemoglobin, and the other 2% is dissolved in plasma. So there's not a whole lot of options for oxygen. It just wants to go into hemoglobin. CO2, I believe it's 73% of it is bicarb. 7% of it is on your hemoglobin. That's not right. Let me think real quick. I have to math. Yeah, no, it's 23% is on your hemoglobin. 7% is dissolved in plasma. And then 70%. Sorry, I had to do quick math. And then 70% of it is bicarb. And this is just through the blood buffer system, right? CO2 plus water goes into bicarb and hydrogen. This is just dissolved in your plasma. This is your hemoglobin. And then these two are not very happy to be with each other in hemoglobin, so that kind of explains that. Okay, hemoglobin dissociation curve. So you have your percent of your hemoglobin saturation, then you have the pressure of your O2. Over here is like 104, where like your lungs, right? And then up here, this would be 100% saturation, and the curve is going to look like this, okay? This is, in clinically terms, the Ocrat point, and that is a technical diagnosis of that name. So basically, like, if you have your PO4 is 104%, right, you're going to be 100% saturated. But then if you get down here to, like, 40, right, I think that this is very poorly drawing. You're, like, 75% saturated, right? So even if you drop a lot in this, you're not really going to drop a whole lot in that curve. But you can have different shifts. So this one that I'm drawing right now is a right shift, and the one in the green is going to be the left shift. Okay, and so if you have a right shift, what this is saying is that it is going to be decreasing my affinity of my oxygen. Meaning I'm going to be shifting into my T state for my hemoglobin, and I'm going to be releasing it, right? Because if I was at here, then you got this much more oxygen release because it's no longer with your hemoglobin, okay? My left shift is going to have an increased affinity of my oxygen, meaning I'm going to be in my R state and I'm not going to want to let go. Things that cause a left shift, or permanent left shift, permanent left shift is going to be carbon monoxide poisoning or fetal hemoglobin. They're going to hold on to the oxygen very well. So now for the things that can affect this. You have something called your cadet. This is your CO2, A is your acid, D is your BPG or DPG, E is exercise, and T is your temperature. If you have an increase in cadet, you're going to have a right shift. And if you have a decrease in cadet, you're going to have a left shift. So decreased CO2 is going to cause a left shift. Increased CO2 will be a right shift, right? And so on and so forth. So that's what my cadet is. Include a description of oxygen heating and factors that influence the affinity. How these... Yeah, perfect. Okay, that's it. Thanks, Jordan. See ya.